Welcome to Tech for Novice, your channel dedicated to technology-related information in simple language. Today we are going to explore home network basic structure to set up our own network without outside help. This is a typical home network with few devices. Actual network could be simpler or more complicated than it, but this setup represents basic structure. Home network is almost universal, but not all of us have confidence to set up our network without outside help. Reason is lack of basic knowledge to start with. I hope couple of videos I am planning will guide network novice where to start. A home network is a group of devices connected together for communication and data exchange. Main advantage of a network is ease of sharing files, printers, storage, and internet connection. Router is the heart of the network, which should be set up properly to safeguard information and connected devices. Interconnection means possibility of intruder with bad intention, such as stealing, exposing, altering, disabling or destroying data, applications, or other assets. In the worst-case scenario, compromised confidential information may lead to financial loss. Installing and configuring a router could be challenging for novice, but it is not an impossible task. Modem is a device that convert internet signal to Ethernet signal for home network use. Different types of modems are required for different types of internet signals transmitted via phone line, coaxial cable, optical fiber, cellular data, etc. Modem usually has only one Ethernet port which can handle only one device at a time. Router is a device that creates a network by connecting multiple devices and manages the network traffic between them and internet. It connects to the internet via modem and manages shared internet access by multiple devices, either through wired Ethernet connections or wireless access point, overcoming the single device limit of a modem. It manages internal IP address to identify connected devices in the network and directs internet and internal traffic to the correct devices on the local network, ensuring each device receives the information it had asked. Network switch can be added to expand single port to multiple ports to connect more devices within the same local network. A wireless access point is a networking device that allows wireless-capable devices to connect to a wired network by acting as a bridge between wired and wireless devices. Wi-Fi router is a router with wireless access point built in. Modem-router combo contains a modem, router, and wireless access point in a single device. Internet protocols are designed for efficient data delivery over long distances, while Ethernet signals used in local network are designed for efficient data delivery over shorter distances. Different types of devices are required to handle entirely different signals, though both can be assembled as a single device. Each device in a network should have a unique identity for communication to determine which device is sending or requesting data. Each network device has manufacturer-assigned unique identifier called Media Access Control Address or MAC address, also known as physical address and hardware address. Each network device using Internet Protocol has a unique numerical label called IP address, which is linked to MAC address. Home network has one public IP address assigned by ISP and one private IP address for each device in the network managed by the router. Public address is globally unique and is used to identify a network on the internet. Private or internal address is not visible outside local network. Router uses network address translation or NAT to map multiple local addresses to a public one for sharing a single internet connection. It is responsibility of the router to keep track of the device asking information to and from internet and sending received information to the device that asked for it using private address for identification. IP address such as 192.168.50.20 has two parts, network ID and host ID. Subnet mask defines the length of network and host sections of the IP address. Subnetting breaks up networks into subnets or smaller networks and increases data routing efficiency and enhances security by isolating compromised subnet. Here we have some examples of how subnet mask defines the network and host sections of the IP address. 192.168.1.35 is the IP address with different subnet masks in these two examples. IP address and subnet mask both have four sections. With subnet mask 255.255.0.0, host ID is 0.0. 1.35 and network ID is 192.168.0.0. Here host part and network part each is occupying two sections of the IP address. With subnet mask 255.255.255.0, host ID is 0.0.0.35 and network ID is 192.168.1.0. In this case, host part is occupying one section and network part is occupying three sections of the IP address. Router first checks the network ID and then host ID within the network while communicating with the device. In the third example, IP address 192.168.1.30 and host ID 0.0.0.0.2 have no common number. In this case, host part is taking less than one section and network part is taking more than three sections of the IP address. Subnet mask determines the number of maximum subnet and number of maximum hosts within the subnet. Home networks usually don't need subnets and therefore can use default subnet mask 255.255.255.0. It makes a network of maximum 254 devices. It is a little bit complicated for novice, but understanding its role is enough without bothering how it works. Wi-Fi protocol use very small portion of the microwave section of the electromagnetic spectrum. Common frequency bands used for Wi-Fi are 2.4 GHz, 5 GHz, and 6 GHz bands. Satellites, radars, and some household devices also use parts of these wave bands. Wi-Fi routers broadcast one or more common Wi-Fi frequency bands 2.4 GHz, 5 GHz, and 6 GHz simultaneously. Each Wi-Fi band is divided into a number of subbands called channels. Range of frequencies occupied by a channel is called channel width. Two or more channels can be combined into a single wider channel with channel bonding. Available channel widths depend on the Wi-Fi standard. Wider channels allow faster data transmission with potential increased interference. Please note that only one channel from each band can be used at a time. 2.4 GHz band has 14 channels, 20 MHz or 22 MHz wide depending on modulation used. They are separated by 5 MHz except channel 14. Channel is identified by its center frequency, which is the center of the channel width. With 14 channels sharing available 83.5 MHz bandwidth, they need to be overlapped. 2.4 GHz band has 4 groups of non-overlapping channels. Group 1 includes channels 1, 6, 11, and 14. Group 2 includes channels 2, 7, and 12. Group 3 includes channels 3, 8, and 13. And Group 4 includes channels 4, 9, and 14. As channels 12, 13, and 14 are not available worldwide, number of non-overlapping channels will be 3 in Group 1 and 2 each in other groups. Therefore, one of the channels in Group 1, that is Channel 1, or 6 or 11, is preferred for avoiding interference. 5 GHz band has 500 MHz bandwidth, including DFS channels. It supports up to 25 20 MHz channels, 12 40 MHz channels, 6 80 MHz channels, and 3 160 MHz channels, all non-overlapping. This band includes DFS or dynamic frequency selection channels used by weather and other radar systems. Use of these channels should be stopped during radar events by automatically moving off these channels. It is better not to use DFS channels if frequent radar activities are in the vicinity. Non-DFS channels are 36, 40, 44, 48, 149, 153, 157, and 161. Please note that available frequency range is not consecutive and available channels depend on specific region. 5 GHz Wi-Fi band includes 3 of the 8 frequency ranges of UNII or Unlicensed National Information Infrastructure frequency bands defined by US FCC. Availability of specific channels and conditions of their use depend on the regulations of each country. 6 GHz band has 1,200 MHz bandwidth. It supports up to 59 20 MHz channels, 29 40 MHz channels, 1480 MHz channels, 7 160 MHz channels, and 3 320 MHz channels, all non-overlapping. With higher frequency and wider bandwidth, this band has advantage of higher speed, wider channels, and no interference from legacy Wi-Fi devices or household appliances like microwaves oven. 6 GHz Wi-Fi band includes 4 UNII or unlicensed National Information Infrastructure frequency bands, UNII 5 to UNII 8. Availability of specific channels and conditions of their use depend on the regulations of each country. Here is the summary of all Wi-Fi bands. Higher frequency generally results higher speed, and wider band supports wider channels, which also boosts speed. However, higher frequency has shorter signal range and lower obstruction penetration ability. Wider channels are susceptible to interference. 6 GHz Wi-Fi band is relatively new, and therefore only few compatible devices are in the market. IEEE 802.11 is the technical standards for wireless local area network computer communication developed by Institute of Electrical and Electronics Engineers, IEEE in short. Wireless local area network is commonly known with brand name Wi-Fi, meaning wireless fidelity. IEEE 802.11 standards have evolved significantly since their inception in the late 1990s. Naming scheme with generation number such as Wi-Fi 5 for 802.11ac, Wi-Fi 6 for 802.11ax, is used for Wi-Fi standards for simplicity. Newer standards use better technology for signal modulation to increase transmission speed and better encryption to enhance security. They also support more channel options and more clients with improved performance. Wi-Fi 5 is the 5th generation of the wireless networking protocol, still popular today. It supports 5 GHz frequency band, 160 MHz channel width, and maximum theoretical speeds up to 3.5 gigabits per second. Wi-Fi 5 supports MU-MIMO or multi-user, multiple input, multiple output. MU-MIMO enables a router to communicate with multiple devices to send and receive unique streams simultaneously. With SU-MIMO or single-user MIMO, router communication is limited to single device at a time, though use of multiple streams is allowed. Use of beamforming technology enhances communication efficiency by directing signal towards connected devices instead of broadcasting uniformly. 802.11ac routers usually include 2.4 GHz band from Wi-Fi 4 and with backward compatibility to earlier generation. Wi-Fi 6 is the 6th generation of the wireless networking protocol. It supports maximum theoretical speeds up to 9.6 gigabits per second. Wi-Fi 6 MU-MIMO or multi-user, multiple input, multiple output, supports more devices and uplink for simultaneous communication. OFDMA or orthogonal frequency division multiple access complements MU-MIMO by subdividing available channel bandwidth into smaller resource units to engage with multiple devices simultaneously, enabling efficient data allocation among multiple devices and reducing latency. Wi-Fi 6 supports target wake time, which enhances battery life by waking devices only when needed. Wi-Fi 6 supports latest security protocol Wi-Fi Protected Access 3 or WPA3 designed to safeguard Wi-Fi traffic. Wi-Fi 6E is an extension of Wi-Fi 6 with 6 GHz band. Wi-Fi 7 is 7th and latest generation of the wireless networking protocol, released in 2024. Additional features on top of Wi-Fi 6E sets the Wi-Fi 7 standard apart from its predecessors. It supports maximum theoretical speeds up to 46 gigabits per second, 320 MHz channel width, and multi-link operation or MLO. With MLO, a Wi-Fi device can connect across 2 or more channels in different bands simultaneously. This is the first time a device can use 2 or more bands at the same time to increase speed and stability. Wi-Fi 7 adds another new feature called Preamble Puncturing. It can bypass channels with interference and add next available channels to transmit data. Wi-Fi 7 includes options for contiguous and non-contiguous channel bands, 320 MHz with 160 plus 160 MHz channels, and 240 MHz with 160 plus 80 MHz channels. Other notable improvements are enhanced MU-MIMO, target wake time, and reduced latency. Data moves in one channel of a band at a time using streams, whose speed is determined by Wi-Fi standard and number depends on router design. Stream speed is the base speed of a frequency band in a Wi-Fi standard. Use of more streams mean more data travel at a time, which translates to higher speed. Maximum theoretical speed of a router is combined theoretical speed of all bands, which is stream speed on widest channel multiplied by number of streams router has for each band. Router speed is expressed in Mbps megabits per second or Gbps gigabits per second. This table shows maximum theoretical speed of Wi-Fi 5 and Wi-Fi 6 on 5 GHz band for different channel width. Let us check data rate of a AX6000 router with 6000 megabits per second speed. It is 4-stream Wi-Fi 6 router whose base speed is 1201 megabits per second per stream with 5 GHz band 160 MHz channel and 287 megabits per second per stream with 2.4 GHz band 40 MHz channel. Router theoretical maximum speed with 5 GHz band is 1201 times 4 equal to 4804 megabits per second. With 2.4 GHz band, it is 287 times 4 equal to 1148 megabits per second. We get 5952 megabits per second after adding the two speeds, which is rounded to 6000 megabits per second. In real world, a fast router doesn't automatically translate to high speed. First of all, Wi-Fi data transmission is half duplex, either sending or receiving data at a time, which reduces transmission efficiency to lower data transfer rate. Another limitation is availability of bandwidth. Only one channel, usually a small portion of one of the frequency bands, can be used at a time with Wi-Fi standards before Wi-Fi 7. Using wider channel for higher speed is also not always practical due to interference. Most of the client devices which support 1 or 2 streams are also reasons for slower speed. They can't take full advantage of higher router speed with more streams. Though individual client device may not be able to take advantage of high-speed routers supporting more streams, it can handle more devices running at the best possible speeds at the same time. External factors also limit wireless speed. Distance from the access point and physical obstructions, such as walls, signal blocking, or reflecting materials affect signal propagation and reduce speed. Higher frequency bands are more susceptible to these obstructions. Another major problem is interference from neighboring wireless networks and devices in the same frequency, which degrade performance. Too many active devices on the same network sharing the same available bandwidth will increase queuing time and reduce speed. We are talking about local network speed so far. Internet connection speed controlled by ISP is usually slower than router speeds, which is another factor limiting internet access speed. Numbers associated with router model could be about speed, but it is misleading as the real-world speed is quite different. It is impossible to estimate expected network speed due to several factors influencing it, as we just discussed. Therefore, typical actual speed shown here is only for reference, which may differ a lot depending on network devices, their location, network structure, and network traffic. Power level of Wi-Fi devices are controlled by regulation, which is another reason for weaker signal at not so far from the router. Thank you so much for watching this video. If you like this video, please comment, share, thumbs up, subscribe, and press the bell icon.